Hello, my dear. I hope right. So, my dear, continue, and we are like that. So now the time is now we are entering second law of thermodynamics. See, if you see, you look, if you tell yourself, think yourself, sir, I have a first law. Why we are bothered about the number first? They are the basic. So, my dear, see, the first law and the second law. The first law gives the quantity. Second second law gives the quality. First law gives quantity. That means first law says that conservation of energy. That means energy will conserve, and energy will conserve. That means conserve. Example, for example, you convert heat work and convert because there is conservation of energy. But the second law says that cannot completely convert heat and cannot convert. Number first. Number second, if you think about the process, so observe very carefully this process. Can observe very carefully for this that observe this. Can observe can observe. First observe this. Okay. Afternoon. Observe this. Very important. Can observe only. Observe this process. What do you think? See, my dear, these are the few practically applied. These are the practical process. Is that a hot coffee cup, a hot coffee? There is a resistor. The current is the potential difference. And this is the hot coffee. The heat will transfer the temperature difference, electricity. So due to, and there is a paddle moving the lowering of its state. So, my dear, if you think about the second law of a thermodynamics, direction of the process. This gives the direction, feasible direction. This gives the feasible direction, which direction the process is possible. But the first law doesn't give any information about the direction. The first law gives the only conservation. That means convert one form of energy to another form. But in which direction the conversion is feasible or it is efficient, that gives. That means quality. This gives the quality. Grade, also grade, high grade, low grade. So there is a hot coffee. A cup of hot coffee does not get hotter in the naturally. These all are the spontaneous process, natural process. Like if there is a hot coffee in a cup and you place that coffee in a room, generally the room is colder compared to hot coffee. The heat will transfer. If we take, this is our system. This is our system. So heat will transfer from the system to the surrounding. That means system is your hot coffee and surrounding is your room. So heat will transfer from the coffee to the room. How? Due to the temperature difference. So automatically there is a direction. it will transfer from high temperature to low temperature. Natural process. But whether it will get hotter again, that means if you transfer heat from this system to this system, surrounding act as a also system, this system to this system, naturally, but whether the heat will again reverse in the direction, obviously no. Obviously no. Why? Because these are the spontaneous, a practical process, natural process. That means this process have a certain rhythms. These process have a certain rhythms. That means in that direction the process will happen. It is not naturally possible to reverse the heat from the surrounding to the system to get the coffee is hotter. First. Number second example, if there is a resistor, if you pass the current, automatically due to the resistor, if you take, this is our system, resistor is our system. So obviously, if the current will flow due to the potential difference V, so due to the current, there is a dissipation of heat from the resistor to the surrounding. Will dissipate. Now, think reverse. Whether it is possible to heat the resistor, thoroughly heat the resistor, and you flow the current? It is possible? No. That means this also a certain rhythms, have a certain direction. That means transferring heat to the wire will not generate. That means one process 1 to 2 is possible. That means if you transfer a current, automatically there is a resistor is heating and it will transfer a heat, yani heat loss. It will lose. Whether heat will lose to the surrounding, whether take that heat from the surrounding to the system, whether the current is flow? No. No current is flow. So these also have a certain rhythms, have a certain direction. Okay? So this is also a natural. Now, third, transfer. See, if this is our system, container, in that container there is a fluid is there, and you stirrer that. That means you stirring. That means rotate this shaft, and due to the rotation of the shaft, the stirrer device, and that is stirring. That means if you lower the weight, in the downward direction, the system will rotate. Stirrer will rotate. And if we take, see my dear, it is not like that. Our system is except stirrer. Very important. See, that's a very important thing, that our system, that means except stirrer device, that means except stirrers, that means stirrer is our surrounding, our system. Except stirrer, this is our system. Now, my dear, if we lower the weight, stirrer will rotate. Let's suppose the property of initial T1 of the system, property is T1. Now, if you stirrer the device, its property will change. Let's suppose T2. Let's suppose T2. That means its property change. You can easily find this T1 and T2. Easily find this T1 and T2. No problem at all. Now, whether, that means in this condition, internal energy will increase and it will release. It will release. Whether you can take a heat from the surrounding, that release heat, You take that release heat from the surrounding to the system, whether the starter will rotate, not. The starter will not. That means transferring heat to the paddle wheel, that means starter device, will not cause to have a certain rhythms. That means, what is this? These are the very practical things and you can observe easily. So you can say that, sir, this is one direction, but there are very complex situations in which we cannot directly judge. So in that condition, second law very helpful. Which direction the process is possible, the process happening. So these are the practical things. That means a cup of hot coffee doesn't get hotter in a colder room, have a certain rhythms. Transferring heat to the wire will not generate electricity, that is have a certain rhythms. Transferring of heat to the paddle wheel will not cause to rotate, have a certain rhythms. That means all the spontaneous process in the nature have a certain rhythm, have a direction. That means all the natural spontaneous process have a irreversible. So this second law gives the actuality. First law gives only the conversion. Second law gives in which direction the conversion is feasible, efficient. Clear? Is clear? Everyone plays? So due to this, we can find like that, okay? Now, what is the observation? Think that if you understand clearly, there must be some cause, some output. The output is the observation number 5. What is that? Read very carefully. What is that? Process occurs a certain, who says that situation gives the information that have a certain, that means one have a certain direction and not reverse. That means all the spontaneous process have a certain rhythms. Your growth is child old. Your growth is not old to child. Your hair color black, white have a certain rhythms. Water will fall from high level reservoir to level rhythms. So these have a certain rhythm. That means a spontaneous process. Who gives the information? Second law says that rhythms. That means have a certain wave process. Okay. Now, second line, the first law placed no restriction on the direction of the process. That means the first law is not sufficient to identify the nature of the process. It only converts the one form of energy to the another form. That means first law places no restriction on the direction. That means it doesn't tell about any direction. So that have a certain restriction. That means what is the limitation of the first law? The limitation of the first law, it doesn't give the any information of rhythms, have a direction, have a feasible process. It doesn't give any information. Okay. Now, third number, satisfying the first law doesn't ensure that the process will act. Very important. Very important line. Very important line. That means, see my dear, let's suppose there we want that there is any process. You know that from this pulse, you want that generate a pulse by taking a two switch. Number first is the first law switch. Number second law. Okay. Now, my dear, if you satisfy the first law, that means you switch on the first law, close it. If you close it, process will actually occur. Process is occur, no problem. If you satisfy the first law, process will occur. But what is mean the actually occur? That means that process is feasible or not, that gives. That means if you want to reach one place to the another place, that have a many way, infinite number of way. To reach from one A place, a B place, you have an infinite number of way. That means if I am in office and want to home, there have an infinite number of ways, finite number of direction. But that means that also a process. Infinite number of process. That means first law, if you on the first law, there is a process. But that process is actually feasible or not, that means which process for me it is efficient or it is easy to move me, that gives. That means if you switch on the first law, the process is happen. But that process is actually happen, feasible or not, you must be. That means satisfying the first law, if you switch on, satisfying the first law doesn't ensure that the process will actually occur. But actually it is occur, actually, but the actual process. Which is the actual process? That means I have a 10 ways from my office to home. There is a 10 number of ways in which there is only one way. I have a efficient, actual. That means I want. That gives the second. That means the second law gives the actual process will happen or not. Important thing. Now, that means what we can say that there is a natural principle in addition to the first law which determines the direction in which the natural process will take place or not. See my dear, if the second law is violated, that means not applicable, it is not necessary that the first law will. That means a actual process will happen, they satisfied both first and the actual process. If you not satisfy the first law, automatically second law is invalid. Off the switch of first law, second law is invalid. But if you off the second law, the first law is not valid. But they doesn't give the actual. By that, I am writing like very important. I am telling you. Very important. That I am writing here. Writing this very important. That I am writing. That I am writing here, beta. When the first law, that means there are a observation, that means note. I don't. That very important note. That number first. What is that, beta? See, a process that violates, that means see, the process that violated the first law, the process that violated the second law is not necessary that violated the first law. Okay, so this line is very important. That means a process that process that violates that violates second law doesn't mean means that violates the first law. Very important. And opposite is true. That means first law, if the process is violated the first law, automatically. But a process violates the second law, it is not necessary that process. Why? Because first law is prior than the second law. Number second, second is very important. A process must satisfy process which process actual. A process must satisfy both first and see beta, if the first law is violated, the process is never happen. The process is never happen, either feasible or infeasible. So the process is happen or not, it must be satisfied the first law, but the actual process happen or not, they must be satisfied the first and second. That is very important. First law only says that yes, there is a conversion. That means the way you can convert these 2, 3, 4, 5 ways. That means I am going from my office to home. There are 10 number of way. That 10 number of way gives the first law. But in the 10 number of way, which number is actual, which number is feasible, that gives the second law. So actually, the process is feasible or not, that satisfies both first and second. This is very important. Okay? This is clear? This is clear? This is very important. I'm telling you, many students get confused here. Sir, what is the first law? If the first law is violated, the second law is violated. Yes, my dear. If the first law is violated, see, my dear, if the first law is violated, automatically second law will cancel. But if the second law is violated, it is not necessary that first law is violated. But the process is feasible or not, that satisfies both first and second. Is clear? This is very important. So, my dear, that is the feasibility. That means the process is feasible or not, only the second law gives the information. That means the second law says that yes. And that process have a certain rhythms. That is called a spontaneous process, natural process. See, my dear, in the nature, everything is irreversible. You make the reversible, you have to do effort. Without effort, you cannot do a reversible. Okay? So everything in a disturbed manner, irreversibility. And extent of irreversibility, how much the process is irreversible, that will measure by the entropy. Second law, you can measure the second law. That means if there is a idealized process and there is an actual process, that actual process is how much deviated from the idealized process. That means extent of irreversibility, that measure. That will measure by the entropy. So entropy is a tool to measure the extent of irreversibility, extent of disturbance, extent of spontaneity. That means how much the system, how the system will, how much the level of the system will disturb, measured by the So if you know this thing, then we will design a device. And the second law, design the two type of device. One is the work absorbing and other is the work deliver and work absorb. There are two type of cycle. One work output and there is work in. Work output, work in. So what is the relation in between that? It gives the better understanding for the second law. Okay, that's it. Heat engine and refrigerator or heat engine are output device. Heat engine are output device, very important. Then are output device. Okay. So heat engine is heat output device. The form of work, very important. Work and refrigerator and heat work in. First we go through the heat. Let's see. Let's suppose this is your heat engine and the engine is engine, refrigerator or heat pump, everything have a running on a cycle. Which cycle, reversible or irreversible, at that time I don't know. Move in a cycle. That means if it moves on a cycle, there must be perform a work. But that work, that means a portion of work output, this is the work output, then gives the work. But that work is not a net work. We want the net work. So there must be some work will be present to operate this engine. So what is the net? That means this out minus in is net work, nothing, work out, work in. Very important. That is the net work. That means a portion of work output. So beta, very important, we have to if you know the what is the work output of the engine, always you show that net, not only. Why? Because output work of the heat engine is consumed internally to maintain the continuous operation. That means this output work have a part of this work will consumed internally operate. That means the portion which is consumed by the engine, how much it will out, that will differentiate, gives the net. Obviously. So precisely this gives the information about net. Now, so there is a heat engine, that means talk about heat. So beta, heat engine, that means there is a heat engine working on a cycle, right, takes a heat to operate, where it will take a heat from the source. I will discuss what is that one. High temperature, take a heat and produce net work, and remaining of the heat will reject a low temperature. low temperature. What is the thermal reservoir? We will discuss. So this is precisely a heat engine. That means, see beta, this is a heat engine operating on a cycle. And what is the cycle? We don't know. Okay. Now, there is an important thing is what beta, which is our system? Our system. This is our system. Heat engine is our system. So, we take the temperature at the boundary of this one. That means pH. So, this temperature is must be pH minus, yes or not? So that the temperature will transfer. And this temperature must be PL plus. So for all the calculating purpose, we take these two temperatures. But due to the reversible, if this is the reversible, that means that is for the very infinite small heat transfer due to the that means heat transfer through infinitely small temperature difference. So in that sense, we can neglect the dTH. So this pH and this L will all the calculation. But actually, what we take a temperature, this temperature and this temperature, all the calculation. That means the temperature at the system boundary. This temperature, it is not a temperature of high temperature body, and this is not a temperature of low temperature. This is the temperature of a system boundary. Keep in mind. Okay. So, what is the first law? If the process is happening, so first law is satisfied. What is the first law? First law for which one? For the heat engine. Heat engine working in a cyclic process. And what is the cyclic process in the first law? Integration of cyclic integration of PQ is equal to cyclic or not? That note this thing. So what is the net heat? QH minus QL. What is that? QH minus L. So this is your H minus. And what is the net work? Yes or not? So W net is equal to QH minus L. Now, if we define the efficiency, this is the first law. Now, if we define the efficiency, that means how the efficient of this engine. If we define the efficiency, what is the efficiency of heat engine? That means what is the efficiency? Generally, people say the output by input. No, this is net output. Net output, very important. By output, net output by, okay. So what is the net output? QH minus QL. What is that? What? H minus. What is the input? What is the input to the system? This is not input. This is not input. And what is the net output? Net output is, what is the net output? Net output. Net output is this one. This is the net output. And this net output is equal to QH minus QL. How? When there is a first. So we can write like that. No. That means find the efficiency of heat engine. Efficiency of engine. What is that? What is the net output? W. This is the net output. What is the input? What is the in? The input. Good afternoon, Atul. So what is that? And this is the important. From where the net we find this one? This is find from the first law of thermodynamics. So this is your first law of thermodynamics. Important. This is your first law. How to apply the first law and second law? The first law. From the first law of thermodynamics, what is that? QH minus. You apply the first law of thermodynamics. Apply the first law of thermodynamics. So this is a very important thing. I'm telling you, this is a very important thing. So why we apply the first law? Why? Because there is a process, and process will vanishes. It is never will happen when the first law is not satisfied. The process will trigger. Process will. There are many processes. If the conversion of one thing to the another form, there are many processes. But that many process, and that is gives the first law. That means conversion. Many process. That means I want to go from office to home. There are many processes. But that process, which process is feasible, that gives the second law. So the actual process is happen or not, that will satisfy both. So this is the first law. Okay. Now, but so that what is that? 1 minus. Important. So this is the efficiency of heat engine. And my dear, keep in mind. So what is the assumption of this equation? What is the assumption of this equation? This equation is valid for both cycle. Very important. Valid for both cycle. That means reversible or irreversible. Reversible or irreversible. It is not mandatory that is for the reversible or irreversible. Why? Because we are not assuming that this cycle is reversible or not. For any type of cycle, this equation is valid. And this is for the cycle. So efficiency, that is the heat engine. Now, so this is the work output. Now there is a system. That means there is a system. Again, we design a cycle, the output cycle, and these are the input. That means we design a cycle for the input manner. So this is also working on a cycle. Which cycle? I don't know, reversible or irreversible. But there are some difference. What is the perspective? What is the difference between refrigeration and cooling? What is the difference between refrigeration and cooling? So refrigeration, cooling, and heat pump, these are three are different. Cooling, you do the earthen pot. You have a mitti ka bartan, earthen pot. That means cooling will done at a minimum temperature equal to the atmospheric temperature. Right. Cooling is the process in which we are reduce the temperature, but that temperature is ultimately limiting condition is the atmospheric temperature, and not below that atmosphere. That is called cooling. What is the refrigeration? That means we maintain the lower temperature below the atmospheric temperature. That means in the refrigerator we maintain the lower temperature. Obviously, in the refrigerator, what is your function of the refrigerator? To maintain the lower temperature from the surrounding, so that the food is long lasting. Okay. So refrigeration, that means we maintain the lower temperature. And what is the heat pump? But these are two different, but both are the ice. So, input. Okay. So what is that? See, my dear, there is a, this is important. Our ice, that means our refrigerator, or no problem at all. And we take, and this is our system. Take, this is our system. Our system. Our system, no problem. Our system. This system, our system. Don't like. our system. Our system. Refrigerator or heat pump, we take a system. Now, this system will operate in a cycle in anti-clockwise. That means this system will operate on a cycle anti-clockwise. Why? Because work observing will take a net input, work in, so net work input. Okay, work in. When this is taking a work, operate the cycle, that work will, and when the work will done, that receive a heat from low temperature body reservoir and reject a heat high temperature. This is the process of the refrigerator. Now, the purpose is that if you maintain this temperature, if you maintain, that means if you maintain the lower temperature, that is called refrigeration. And if you maintain the high temperature, that is called heat. That is called heat pump. So, if you maintain, this is your heat pump. If you maintain this one, this is called refrigeration. And this is your refrigeration effect. QL is a refrigeration. So, my dear, in this case, we cannot define the performance. What is the performance? What is the coefficient of performance? Please, anyone? What is the coefficient of performance? What is the difference between efficiency and performance? What is the difference between, very important, what is the difference between efficiency and performance? What is the difference between efficiency and performance? Efficiency, that means what? No. Sir, source temperature and temperature from where heat is rejected are so. No. See, the source temperature. The source, no. This will take this temperature. That means system boundary temperature. That means we take pH and from here, this is the system boundary, PL H plus PL minus. This is, I think you are asking like that, okay? Sir, source temperature and temperature from where the heat is rejected is same. Why? Same is not same. It is not same. Source temperature, okay? This is your source temperature. High temperature is the source, and temperature from where the heat is rejected. No. I'm not getting your question. Source temperature. This is, I think you are asking like that, okay? You are asking like that. No. The source temperature and temperature from where heat is rejected are same. Why? No, not the same. That is the system boundary temperature. That means we are working on this temperature limit. Okay? So, what is the difference between efficiency and performance? The efficiency is defined net output by input. That means what is your output? What you have to output, net output by taking a resource. That means what is your resource and what you give the net output. Net output. What is your resource? You're taking that resource and give the net output. That ratio, that means that ratio will define the efficiency. But the performance is another thing. Performance, what you want and what to do for it. What you want and what to do for it. That means what you want and what we pay for it. That is, so performance or efficiency are two other things. Performance measure the desired effect. What we want and what we pay for it. मतलब हमें क्या चाहिए, हम उसके लिए क्या कर रहे हैं. That ratio is called performance. That means what we want we want divided by what we pay for it. What pay for it. That's it. That is the performance. So generally, we'll take source and sink temperature calculation, but there are not. Yes. Why? Because you're right. Actually, we'll discuss in the entropy chapter also in the next session. Yes, you are very right. What is that? See, if you calculate on this basis, what is that? This is our system. First, this is our system, and these are the system boundary temperature. So the heat, if you calculate the, if you define a system and to define a system boundary, that is boundary, and what is the heat? Heat will transfer and heat will responsible. That means if you want the temperature of the system, to calculate the transfer of heat, we take always system boundary temperature. But in general, we have to do a reversible manner. That means externally reversible. To want the externally reversible, that means heat transfer through a finitely small temperature difference. In that sense, delta TH tends to 0 and delta TL tends to 0. So in that manner, we can take TH and TL. Otherwise, conceptually, we take TH plus DTH. Why? Because we don't know the system is reversible or not. But if the system is total reversible, that means external or internal reversible, in that manner, we can DTH is very minimum, infinitely small temperature difference. So you can it will tends to 0. So in that sense, we put the source temperature and sink temperature. I think Atul, it is. Otherwise, conceptually, we put this temperature. That is damn sure. That means we have to calculate on which temperature basis. Someone asks you on which the calculation of this performance or efficiency of this engine, on which temperature basis. You always take system boundary temperature, number first. But if the system is reversible externally, you can take that TH and TL. Why? Because conceptually, H tends to DT. So what we want and what we pay for it. So what we want, so if we want COP of, define the refrigerator. So what we want in refrigerator, what we want? Refrigerator, we want Q. Want QL. What we want? QL. And what we pay for it? And COP of heat pump. What we want? What we want? H. What we pay for it? Okay. Clear? Now, if you divide this one, no problem. If you divide, you add something, anything. In the previous year, just current year question, they are asking that what is the ratio of heat pump and COP. So for that manner, if you divide COP of refrigerator, and that means divide like that. Of refrigerator by of heat pump. This type question asking 1 mark. What is the COP of refrigerator? What is the COP of refrigerator? QL divided by W in to W divided by QH. So this W in cancel, and that is QL by QH. Very simple. Very simple. Now, and the cycle is reversible. They said the cycle is reversible. Okay. Cycle is reversible. That means it is reversible externally or internally both. If the cycle is reversible, that means for the absolute temperature scale concept of absolute temperature scale, QH by QL is equal to H by. This equation is valid for only for the reversible cycle. This equation is valid for only for the reversible. So put here TL by TH. So if you know the information of lower temperature and higher temperature, you can easily find the ratio of. So my dear, TL is always, that means this is value always less than 1. Yes or not? This value is always less than 1. Yes or not? TL is generally lower than TH. TL is generally lower than TH. So this value, that means COP of refrigerator must be less than C. This is very important. And how much it is less? That means if you want that equal, you add this one. That means COP of heat 1 is equal to 1 plus COP of refrigerator. This is very important. If you want the equalize, you can prove it also. If you want the equalize, you add something. That means if you add COP of refrigerator plus 1, then it is equal. Also important. That means COP of pump minus COP of refrigerator is always 1. But that is valid for see, my dear, this equation COP of refrigerator plus 1 equal to COP of heat pump, any process, either reversible or irreversible cycle. But this equation is valid, this information, this one, TL by TH. This will COP of refrigerator by COP of heat pump is equal to TL by TH, only possible for reversible. Why? Because you equalize the two of heat. That two ratio of heat is nothing according to the. Okay, this is a very important thing. So these are all also we can prove it, no problem. Now, so COP of heat pump, okay. Now, very important. The very important thing is thermal. Very important. What is the thermal energy? See, my dear, the things of energy. And which type of energy? Thermal energy. That means that contains have a energy, heat. So hypothetical body. These are the hypothetical body. Mind it. Not actually. We can develop. We can model. Thermal reservoir is a model. We can model it. How will this just discuss? First, listen. Hypothetical body with relatively large. That means we have to develop, we have to design a body, or reservoir that have a relatively large. Why there is a relatively? Relative, what is the mean by relatively? Relatively compare. That means larger and smaller. These are terms have a relativistic term. That means I am larger. But I am larger is the relativistic from whom? I am intelligent. This is the relativistic term. So these are the relativistic. Larger, smaller, these are things are the relativistic term. So larger from whom? From where the heat will supply, the heat will take. That means if the body will design and that body have a relatively larger, that means from that they are rejecting the body, they are rejecting the thermal energy that are rejecting and thermal energy that are accepting. Energy that have a large energy content as compared to from where they are laboring or taking. Okay. So relatively large thermal energy capacity. And what is the thermal capacity? You know about that? What is the thermal energy capacity? What is the energy capacity? I am asking you, what is the energy capacity? Energy content of that body. That means a body have there is a body, how to measure the energy? Very important. Mass into specific heat. What is the unit of a specific heat? Kilojoule per kg Kelvin. What is the mass? Kg. So per Kelvin. So joule is the energy per Kelvin. So mass into a specific heat, yani M into C This M into C is nothing. This is the energy, thermal energy. That means energy capacity. Energy. This is our energy capacity. The body, that means, see, if this is a container. In this container there is a liquid, water. And that water, how much energy? The mass, you can measure the mass and you have, what is the thermal capacity of the, what is the specific heat? What is the specific heat of that water? Multiply it, you can easily got the, what is the energy? What is the energy contained within the water? So energy content, which energy? Thermal energy. So thermal energy content capacity, this is the content, this is the stored form. Mass into specific heat, these two terms, these two multiply, that gives the thermal energy capacity of that body. That can be supply, that means this body can be supply or absorb finite amount of heat. Finite. That means it will absorb or deliver finite, not infinite, a small night, large, finite amount of heat without, this is very important, without changing the temperature of this body. That means you have to design a body of energy M into C, and if this body is able to supply the heat, during the supply the heat, that means rejecting the heat, its temperature is fixed. Temperature is fixed. That means that is called energy. That means energy reservoir, it is a energy, tremendous amount of energy that have no change its property in the form of temperature, and no change in its property, thermal property, temperature, while rejecting or accepting the heat. That is a tremendous of energy. That means you cannot able to change this body temperature. If you not able to change this body temperature, that body model is thermal energy. The reservoir. That means reservoir is the, what is the reservoir? Reservoir is something to reserve of a quantity. Water reservoir. Water reservoir. Water reservoir, that means reservoir contain the water. Energy reservoir. That means thermal energy reservoir. That means that a reservoir contains a thermal energy. And thermal energy is very much precisely defined by the temperature. That means this have such a high amount of a temperature, so that if you rejecting it or it will accepting it, it's not able to change its temperature. Not able to change. That is the higher thermal. So if it will deliver this high thermal energy, if will taking without changing its temperature, low temperature. So there are two types of reservoir: low temperature reservoir and high temperature. High temperature reservoir always gives, what is give? Reservoir is a thermal, so it always give heat, not work. So first, lower thermal reservoir, that means always accept a heat. But during rejecting or accepting the heat of a body, it's not changing its temperature. That is called thermal reservoir. So any change in temperature, such a body is called thermal energy. Thermal energy reservoir. What is the model about? This is very important. Very important. What is that? A large body of water. A large body of water such as ocean, lake and rivers, as well as the atmospheric air. These act as a reservoir. That means if you take a model, if you take a ocean of a water, if you take a lake of a water, a river of a water, any fluid, and in that fluid, if you take out the some fluid in that means you take out the some quantity of a matter, that system, the matter will very minimal change its property. The atmospheric air also acts as a reservoir. Now, this is second number. What is that? two-phase system. What is the two-phase system? That means the system will change its phase. That means liquid plus vapor, vapor plus what, liquid, liquid plus solid, two-phase system. That means in that the system change its phase. Since system is change its phase, and if system will change its phase, liquid plus, if the system have a liquid and it's converted into vapor, so it's change in phase. Two-phase system, liquid plus vapor, two-phase system. So two-phase system act as a, that means there is a container. This is a container. In that container there is a liquid and there is a vapor. So this is act also a reservoir. Why? Because when you take a heat or give a heat, its phase will change, and during the phase change, constant temperature. No change its temperature. That means this is able to reject heat or absorb heat. That means liquid will convert it into vapor. Liquid will convert it into vapor. Will take heat. Vapor will convert it into liquid. Will reject heat. While taking or rejecting the heat, this two-phase system have a constant temperature. So that this is act also a thermal. The beauty. This act also a thermal reservoir. That means two-phase system. Ultimately, what is the motivation? Motivation is that you can take or reject, you can take or liberate, you can add or reject heat without changing its temperature of a system. That system is industrial furnace. Industrial furnace is also act as a thermal energy. And see, this is the model. Last we will take a model. You can design thermal reservoir by your own choice. There is a large room. There is a large room. In that large room, there is a TV set. There is a TV set. And in the during you have a TV set, you watch the TV, there must be a heat will generate from the TV. But that heat will not able to hot the air inside the room. That means during that heat will rejection, the room temperature will doesn't change. So in that condition, room is a reservoir. Very important thing. Very important thing. That means the air in the room, for example, can be treated as a reservoir. How? In the analysis of heat dissipation from the TV set into. That means we can model anything as a reservoir. But ultimately, the thing is that if you model the thing as a reservoir, keep in mind that model have a same temperature after taking or. So in the room there is a TV set. If the TV set will reject a heat, the room temperature doesn't change. So in that case, the air in the room act as a this is. Okay, so these are the concept of reservoir. Now we can think like that. So beta, see, very important last thing. What is that? Last thing, I will give some concept for that. See, if let's suppose this is a thermal reservoir, our system. Let's suppose this is our system, and M into C, the thermal reservoir, such that it will reject a heat. Thermal reservoir at TH temperature, high temperature, and the surrounding which is rejecting it L temperature. So TH is very high, that means higher than TH, so that heat will reject. So what is the heat will reject? Q is equal to MC to delta T. And what is the delta T? H. See, my dear. That means the energy, thermal energy is equal to Q by delta T. That means This is the large energy capacity. That means this is high. You're high or not? You're high. And if you want the finite heat transfer, we want that high zone. So finite, it must be this temperature. That means change in temperature. Change in temperature. This is delta T, but this temperature is this one. That means this will change temperature is this one. That means is mc dt. dt is for what? This is very important. Don't confuse with. Don't confuse. dt, th, initially th1, and after rejecting heat, let's suppose h2, th1 minus t. That is. Now, see my dear, that means delta T tends to 0. Very minimum, so that we can design a high energy content. In a thermal energy reservoir have a high content of energy. So delta T tends to 0. Delta T tends to 0. That means temperature approx. This logic. How to design a thermal reservoir. So if you take a temperature approximately constant, so that you can design a very high thermal energy. Otherwise not. So this is an important thing, how to design very high. That means how to model that the energy reservoir have a large capacity only if the energy reservoir have a constant after rejecting or accepting. This is clear. This is proved. That means the energy, the reservoir, this is called reserve. This is reservoir. That means reserve this energy. And this reserve of this energy have called thermal energy reservoir. While rejecting heat or accepting heat, it is damn sure the thermal reservoir have a not change approximately. That means this is called clear. What is the concept of thermal energy reservoir? What is the concept of thermal energy reservoir? It is clear, beta. So this is the concept of thermal energy reservoir. Okay. Now we'll discuss in the next session. No problem. In the next session, we can discuss the Clausius inequality also and entropy also. Okay. Up to that, this is the sufficient amount of content which I have to deliver today. And we think the basic things. What is the basic thing? That energy reservoir. What is the process? All these things. Fine. Next session. Thank you. Bye bye.